Hi everybody, welcome to another video in Calculus 2, Section 10.2, Sequence. So previous section 10.1, we studied about two things, sequence and series. Sequence is a list of individual terms, whereas series is the sum. And when we say series, we mean infinite sum, meaning add all the terms in the sequence. Now this section we focus only on sequence, meaning a particular term of the sequence. Right. So the first theorem, it says if the function is equal to a term of the sequence when n positive integers, or we should even like that whole numbers, it doesn't matter. When we say the limit of the function is the same as the limit of the sequence, because that, like we already did this before, we already used this before. So the limit of a sequence is the limit of a function. So limit of a sequence, limit of a function equal limit of sequence. However, we're just going to write the limit in. When we do this, we don't need to convert to a fraction, convert to a function and then do the limit. Just go ahead and just use that as a function of n. So what I mean is, we don't need to say h of n is equal to that. Let f of x be equal to h of n. We don't have to start with that. We don't have to introduce a function f. We're just going to use that term directly. Right, so determine the limit of the sequence if it's this. So it's limit of the sequence. By that we mean limit at infinity when n goes to infinity. Right, so that's simple enough. And we did this before, right? For polynomials, only the one with the highest power matters. And comparing n and 1, the 1 is negligible as n goes to infinity. And that equal to 1, or we even write limit of 1 equal to 1, because there's no place to put in n. That's simple enough. Next, determine the limit of the sequence. So the limit of the sequence as n goes to infinity. Yeah, we don't even say it when n goes to infinity here. So 3n cubed 2n to the 4th plus 1. So similar to the last problem, we take the one with the higher power. The one with the highest power counts. And then when we simplify, we have 3 over 2n. And the top is finite, the bottom is infinity. Finite over infinity is going to be 0. So I'm just going to put this here, finite number, positive or negative, doesn't matter. But we have the finite divided by something that approaching to infinity. Positive or negative, doesn't matter, will be equal to 0. Finite amount divided by infinity is 0. So next, we have this. By the way, you see something similar to this in limit, derivative, integrals, and now summation. So pretty much say limit of a sum is the sum of the limit. Limit of difference is the difference of the limits. Right. We can take the constant outside like we did with integral. Limit of product is the product of the limit. Limit of the quotient is the quotient of the limit. Except, yeah, just make sure that we don't want to divide by 0. That's all. I put semicolon here. Right. So like I said, there's nothing new. Also, talk about nothing new. This is also nothing new. Since we're trying to find the limit, quite a few of the problem. So if we have something that in indeterminate form, we're going to use the Hospital rule. Right. So in terms of, like I said, that is anything in indeterminate form. It could be in this exponential form. If it has the exponential form like that, we can just take ln on both sides, and of course the routine is still the same as we did before. Right. And then the growth rate. Now this is very important. We'll go back to this a few more times. But it said something grow faster if we put in a ratio. The ratio, if the top is bigger, this go to infinity. If the bottom is bigger, it go to 0. It go to anything in between. We say they have comparable rate. So think about this. We will have a ratio. If the top is extremely big, like infinity, then the whole thing go to infinity. Now, if we have a ratio again, the top is finite, the bottom is indefinitely big, so that go to 0. So the top is big, it go to infinity. The bottom is big, it go to 0. If the ratio is anywhere in between 0 and infinity, then then the function have comparable growth rates, and the growth rate here, of course, is the rate where it goes to infinity. That's the way we define it. Right. And there's the notation for that. We use that notation to denote it grow faster. Yeah. And we have this ranking that. So let's elaborate a little. X to x, I think this is called the tower function, right? Anyway, I think we mentioned that in section 7.6. This b to the x, and this is x to the p. B to the x, this is exponential function. And x to the p is, let's say, called a power function. And within the power of, we have x squared significantly less than x3, and then so on. So the bigger the power, the bigger, I mean, I should use that simple. And in the exponential, like 2 to the x, significantly less than 3 to the x. So the bigger the base, the faster it goes to infinity. So within each one of them we have those. And then the power function is bigger than the ln in general. Right? So x raised to any positive power is going to be bigger than ln. And we have p, q, r, s are positive. So positive p, q, r, s, and then b is greater than 1. the base is bigger than 1. Right. So those are the roll rate. It will be extremely important when we do this. Right. Not the first one though. So it says determine the limits of the following sequence. We have 2 examples here. So first, find the limit of this. So this looks something like we did in section 7.6 because it has the power form. When n goes to infinity, the 5 doesn't matter, right? Because the n is a lot bigger than 5. So we have n over n is 1. So we have 1 raised to infinity. So this is 1 over infinity indeterminate form. So in that case, usually when we have something like this, we take ln on both sides. But before we do that, I want to simplify a few things first. Let's split this and write 5 over n and n over n. Let's also say 5 over n is 5 times n to negative 1. Because we're going to use L'Hopital rule, which means we take derivative. It will be more convenient to write that as a power. N over 1, n is 1. Right, so we use this instead of that. Right, now. First we're going to say let y be this. Now we let n goes to infinity. Right, it is indeterminate form, so we will take ln on both sides. That indeterminate form, anything that has the exponent, we should take ln on both sides. And I put ln inside of the limit. With that, we can take exponent outside. Now, in order to do use the L'Hopital rule, we need to have a ratio of 2 functions. So in that n, by default, we can say n to the first power, right? So move to the bottom, it becomes negative 1. With that, we can use the L'Hopital rule. The L'Hopital rule involving that we take derivative of the top and derivative of the bottom. Derivative of the bottom is negative n original power minus 1, so n to negative 2. Derivative of ln is going to be the reciprocal function. And then the chain rule say we have to take derivative of what inside. So we still have 1 over 5n to the negative 1 plus 1. Sorry, I forgot the derivative of what inside. Yeah, start the chain rule. Right. So the derivative of this is negative 5 n to negative 2. It is multiplied to it like that. Now, so here we can say the negative n to negative 2 cancel, right? Because just multiply to it, and the negative here and the negative here also cancel out. So we just have 5 left. And then nothing at the bottom. So we're going to put 5, I'll just write like this first. I'm going to put 5 on top. And then the n minus 1 at the bottom. Now n goes to infinity, finite divided by infinity, so this one goes to 0, and n goes to infinity. So bottom line is we have 5 at the top, 1 at the bottom, so this is 5. Now if ln of y is equal to 5, we can take both sides raised to the e power. Exponential function. In ln cancel out, so we have y, which is the limit, is equal to 5. E to the 5th. Sorry. Those cancel out. Y go to e to the 5th. So that is the sequence approaching to e to the 5th power. Or we just said limit at n goes to infinity of b of n equal to e to the 5th. Right. Next, let's find the limit of this sequence. Right. Sorry, we're going to have the ratio later, but for now, just have to copy it first. Right. So negative exponent moves down, turn to positive. Right. Now, of course, we put n in, we have infinity over infinity, and that is the Hospital rule, right? So take derivative, the top, the bottom. Take derivative of the top, the power decreasing to 9, and then use the Hospital rule again, and then just keep doing that 10 times. The bottom, doesn't matter how you take derivative, the bottom will stay e to the n. Where you take derivative of the top repeatedly, the power of n is decreasing. Right, so of course we can do that, but that n to the 10 power, meaning we have to use the Hospital rule 10 times, which I don't want to do. What we do instead is refer to the ranking that we have earlier. Exponential function is grow a lot faster than the power function. So this is the power function, exponential function. E to the n is exponential function. and in the ranking the power function is significantly less, grow a lot slower than exponential function. So we have n to the 10 is significantly less than a sub n. Now think about this. We have a ratio. The top is extremely small compared to the bottom. So what do you think this one goes to? So once again, the top is significantly smaller than the bottom. Or we think about this. We talk about roll rates. So the rate where the function goes to infinity, e to the n will go to infinity extremely fast compared to that. So the bottom goes too fast to infinity compared to the top. So in which case we say this goes to 0 because the top goes to infinity too fast compared to the top. If the top goes faster to infinity, the whole thing goes to infinity. But this time the bottom, e to the n, go faster to infinity because exponential function go faster to infinity faster than the power function. So let's just write out this because we will use this later. So we have actually we start with ln of a number. Ln will be less than any exponential, any power function. Sorry. Let's do this again. So ln is less than, I should not say less than, it's lower than power function, and power function is slower than the power function times that, and then we have exponential function. And then we have the tower function. That's just shortcut, but there will be a few more of this. So if we have the smaller one divided by the extremely big, and that will go to 0. Or if the bottom goes too fast to infinity, the whole thing goes to 0. If the top goes too fast to infinity, that will go to infinity. Right. Next, more terminologies. We say the function is increasing if it is the next term is bigger than the previous one. By the way, when we say non-decreasing, it has the equal sign. And decreasing is less than, non-increasing is less than or equal to. So just the way we said it, it's less than equal to. Of course, non-increasing meaning everything but increasing. Right. Now, if it is either non-increasing or non-decreasing, we call that monotonic, meaning they can only go in one direction. It could be flat or up, but it cannot go down. Or it can go flat or down, but cannot go up. So it cannot be, I should say just either non-increasing or non-decreasing. So it could be equal to in the monotonic, but it cannot go to the opposite direction. Right. So bounded above, if there's a number bigger than every terms in the sequence. Bounded below, if there's a number that is smaller than every terms in the sequence. By the way, it doesn't have to be that number. The bound, there is a number m. So the bound cannot be, it doesn't have to be unique. Like if I say everything is less than 5, that statement I could say is, if everything less than 5 is certainly less than 6. So both 5 and 6 are a bound of of the sequence. Yeah. So the upper bound or lower bound are not unique. Right. Let's find some of them. Determine the sequence. If the sequence bounded, if so, find the limit. Right. So 1 over 1 over n. So usually when we do this, let's just write out a few terms and see what happens. Usually I did not ask first for the limit. If we ask for the limit, that will be easier, but here it is 1 minus 1 over n, right? And then we have the first 4 terms somewhere right here. About fraction, right? 1 over 1 minus n. Right. By the way, is that the same as? It is the same. It's the last example in the. Where did I put it? The same as that summation, right? 1/2, 2/3, 3/4, and so on. So if we write this out, we start with 0. By the way, this is a sequence, not a series. So these are individual terms. If this continue, of course, this is going to go to 1. Right? But it's not going to be bigger than 1. So we say 1 is the bound of a sub n. Or if you don't want 1, we say 5. Of course, if it's less than 1, it's certainly less than 5. They only ask us to find a bound, not the lowest or the smallest upper bound. So in that case, we say 1 over 1 minus n is going to less than 1. For finite n, it could be less than or equal to 1 if we're including when n goes to infinity. So in this case, m equal to 1. Right. How about plus? Plus. Okay. Right. So we start with let's see, fraction 2. 3/2, 4/3, 5/4. If this continue, we're going to have n plus 1 over n. Right? The top is 1 more than the bottom, always. Make more sense if we write 2 over 1. And that goes to 1. Both of them goes to 1. However, a sequence is bigger. All of them are bigger than 1. All of this term less than 1. So the limit of both sequences go to 1, but one of them is getting smaller and smaller to 1, and one getting bigger and bigger to 1. And so we should answer the question, yes. So is the sequence bounded? Yes. So, and the numbers. No, this is a very bad question. Yeah. So be equal to. So yes, we say the sequence is bounded. And we can say an upper bound equal to 1. There may be more than 1. And same thing here, the sequence is also bounded. But this time we have a lower bound. Is equal to 1. Next, compare and contrast the behaviors of n to 3/2 over n 3/2 plus 1 and then with the minus 1 to the n. So the difference of the two is this one. So what is the significance of that? Right. Let's just find the limit. We'll see, right? Right, so I'm going to find both limit a sub n and b sub n goes to infinity. So when n goes to infinity. Now same thing that we said before, right? The highest power term matters. So take that on the top, keep that on the bottom. And so we just have 1. Equal to 1. So we have limit when n goes to infinity a sub n equal to 1. Next, how about b to the n? So the only difference is we have the negative 1 to the n power. By the way, it doesn't matter if it is 1 or negative 1, it is still a constant. It doesn't have n in it, right? It has n on the exponent, but the value is just negative 1 and 1. So let's just say, let's write that instead. So negative 1 to the n power. It will be equal to, when n equal to even, it's going to be positive. And it is equal to negative 1 when n is odd. So after all, just 1 or negative 1. So doesn't have any power, so we still take the highest power on the top and the highest power at the bottom. And that cancel out, and we have limit which the same thing as that, equal to 1 if n is even, and negative 1 if n is odd. Because of that, this limit does not exist, because it is changing from positive to negative. What we call this is called the oscillation, and the limit does not exist. Right. So the behavior, the bound is still 1, or could be -1, but this one, the limit does not exist because it's alternating at 1 and -1. We don't know which one which. And then on this one, there's the limit equal to 1. Right. More theorems. Geometric sequence. Most importantly, in this case, later on we will have a geometric series, but this is a geometric sequence, meaning just one term in the sequence, not talking about the sum. Let R be a real number, easy. Then R to the n equal to 0 if absolute values of R less than 1. Absolute values of R less than 1 is the same thing as saying it is between -1 and 1. Equal to 1. If R equal to 1, it is equal to 1. And if it is greater than or equal to 1, it does not exist. If R greater than 0, then it converges or diverges monotonically. If R is less than 0, it converges or diverges oscillationally. If R equal to 0, then it's just 0, right? 0 raised to any power is still 0. So it is a constant. So we're not talking about that. Right. So I leave some space here so we draw a line and summary about what we have. Right. I say 0, -1, and 1. Right. It says that anything above 0 is monotonically, meaning that it will not jumping up and down. Those are called oscillation. So I say from here on, from 0 and on to infinity, this is monotonic. And anything on the other side is oscillation. Right. Next, within -1 and 1 is convergent. When it is greater than or equal to 1. So this one including the 1. Divergent. Including -1. Is divergent. Between -1 and 1, not inclusively, is convergent. On the outside, divergent, inclusive, including the 1 and -1. anything less than 0 is oscillation, and greater than 1, greater than 0 is monotonic. The sign will not change. That of course only for r to the n power. Right? And r equal to 1, it is a constant. R equal to 0 is also a constant. But that's not really important. Right. Now let's look at this example. For the limit of the following sequence, and because this one come right after what we have in the geometric sequence, so that's why we should use that. Right. So this is 3/2 to the n power times 2. Now doesn't matter if we have a 2 or not. If a sequence is convergent multiplied by 2, it is also convergent. So we have 3/2 to the n power. So now we have r to the 3/2. This one goes to, if we have that term, then the limit of this goes to infinity, or the limit of that does not exist. I said we worry about the limit. For that, since r is bigger than 1, let's say equal to, it doesn't really matter. If that is the case, r to the 3/2, limit of that does not exist. Or we say it is divergent. So this sequence, or we multiply by 2. Multiply by 2 doesn't really do much, but when we do that, this sequence are divergent. However, I mean not however, but in addition to that, in addition to being divergent, the ratio is bigger than 1, so this is, we say, diverges monotonically. Next, we have compared to the form of r to the n here. I don't know why I write r to the 3/2, which is completely off. That's, sorry. R to the n power. Sorry, that was just compared to r to the n power. R is equal to -1/3. Now, -1/3 is between -1 and 1, right? Or we say absolute r less than 1. If it is the case, then this is what's that? It's convergent and go to 0, right? If absolute r less than 1, r to the n go to 0. Right, so if absolute of r less than 1, the limit goes to 0. Now, if it go to 0 and we say it, so we say that the sequence has the limit and that equal to 0. So r to the n, if r bigger than 1, diverges, or less than -1 also diverges. Now this one equal to 0, or if we want to write that, we say the sequence converges because it has the limit, converges, but this is less than 0, so we say converges oscillation by oscillation. So if it's positive, monotonically; if it's negative, it's oscillation. Of course, like I said, we don't have equal to 0. Because 0 is just a constant. Anyway, so we need to rewrite like this, so we have the r to the n power. So to do that, I'm going to write r2 to the 1 over 3 to the n. Now, 1, we can say r to the n power. And we can bring both of 1 and 3 inside. And that's what we have. Now comparing to r to the n power. Since r equal to 1/3, which is less than 1. Of course, if it's less than 1, we can also say absolute values of it less than 1. So this is the case. So the limit is equal to 0. Now, if that equal to 0, multiplied by 2 will be equal to 0. Keep doing that. Since that one goes to 0, multiplied by 2 is still 0. So I will take the 2 outside. And limit of that is 0 times 2 is 0. So we say this sequence converges because it has the limit. And since r bigger than 1, this is converges monotonically. So just like that. Not sure how I need space here. Now what we have next is the Squeeze Theorem. If we have 3 sequences in order a sub n less than or equal to b less than or equal to c sub n, this is less than or equal to and not those signs. Right. So we said if the left side goes to n, I go to L, the right side go to L, the middle goes to L. So I'm just going to say if this go to L, so the middle have to be L as well. So that just like the Squeeze Theorem. Right. I'll find the limit of this sequence. Of course, this example right below the Squeeze Theorem, that means we have to use it. So in order to use the Squeeze Theorem, we have to write some inequality in this form. And luckily, it's cosine, and we know sine cosine is the wave, and it is between 1 and -1. Right? Now if we just divide by n square plus 1 on both sides. Right. Usually we don't want to do that because sometimes divide by the negative power reverse inequality, and when we divide by 0 it is undefined, but we don't have to worry about that here. And by default the sequence n start from 1, 2, 3 and so on. So if n is positive, or actually in this case n could be anything, doesn't matter, n squared is not going to be negative, plus 1, so the bottom is going to be positive. Divide by a positive number, we do not reverse inequality, even though if we do, it's still fine. If we reverse it, that term is still in the middle. Okay. But this case is positive, so inequality will remain the same. Right. Now, the next is easy. We take the limit of each one on the left, on the right. If they equal to the same thing, the middle has to go to that as well. So take n goes to infinity for negative 1 over n squared plus 1. And like I said, n squared plus 1. The plus 1 is insignificant compared to infinity. So finite on the top, infinity at the bottom, 0. Now we find the limit on the right. Now put infinity, the 1 also insignificant compared to n. Even n squared is even bigger than n. That cancel out. Finite on the top, infinity at the bottom. This one go to 0. Now the left goes to 0, the right goes to 0, so the middle goes to 0. Yeah, burn out the space, so I just write like that as n goes to infinity. So what we learned earlier here is that it doesn't matter if it is convergent, multiplied by a constant, still convergent. And then here we have the Squeeze theorem. Right, more theorem. A bounded monotonic sequence converges. So that means whether width is increasing or decreasing or non-increasing, non-decreasing, it doesn't matter. If it is monotonic sequence and this is bounded, there will be a maximum or the minimum, or I should say there's the limit for that sequence. Right. Then we have the growth rate again. And we mentioned before, this ranking do not change if a sequence is multiplied by a positive constant. So not only that, the sequence convergent or divergent does not affect by multiplied by a constant. The ranking here also do not affect by multiplied by a constant. So when we look at this, which one faster? Which one go to infinity faster? And this is the short version of that. Right, so ln n to the 10 power, right? Can take the power outside. And then the other one is 0.01 to the n. Now, for this, according to the theorem, we said the constant in front does not actually affect in that. So now we just compare an ln of n and n. And we know that n to the p is the power function. If we choose p equal to 1, we have that. And then we have ln. And ln is less than, significantly slower than the power function. So we say ln grows slower than n raised to any power, In this case, we choose 1. Any positive power here, so we choose 1 here. So if that is the case, it doesn't matter if we have a constant in front. Does not affect this ranking. So multiply 10 here and multiply 0.01 there. It's still the same. So in that case, we say this one goes faster to infinity. Right. So compare the rate. That's what we have. Right. Next, n factorial and 10 to the n. Well, yeah. Now we just which factorial, then super exponent. Right. So this case, the factorial is bigger than the exponential, but less than the n to the n function. Right. So n to the n and 10 to the n. We have this ranking. Factorial is bigger than any exponential function. So once again, the ranking ln, power function, exponential function, factorial, and n to the n. So in this case, factorial go faster to infinity than that. And even though if we have a constant like multiplied by 2 or multiplied by any numbers here, does not affect the ranking at all. Again, ln, power, exponential, factorial, and that I think is called the super exponent or tower function. Right, next, 3 times 2 to the n and 2 times n cubed. So, like I said, the constant in front of it doesn't matter. What matters is comparing n cubed and 2 to the n. So which one faster? So, n cubed, that is power. 2 to the n, that exponential. So exponential function always greater than power function. So that one is greater n cubed because power function grows slower to infinity than exponential function. So with that, multiply by 3, multiply by 2 doesn't affect in it. Wait, I wrote that wrong. Right. So n cubed, the power is significantly slower when it go to infinity compared to 2 to the n. So for 2 to the n, we multiply by 3. So 3 times 2 to the n. It's going to be bigger when we multiply this by 2. Right. So multiply by the constant in front doesn't affecting the ranking. So exponential function go faster to infinity than power function. So keep this ranking in somewhere close to you because we prefer this many times. Right. Once again, the ln, the power function, exponential function, and then factorial, and n to the n. Right. Now let's elaborate for the power function. For a power function, the bigger the power, the bigger the function, obviously. For the exponential function, the bigger the base, the bigger the function. And then factorial, and then that. Right. In the power, as in bigger power, bigger function. And in terms of exponential, bigger the base, bigger the function. So in which case, if I have to ask where we have the long list of so we have this ranking. The constant does not go to infinity, so that one doesn't count. Ln of x, x square root is x to the 1/2. So in the ranking, x to the 1/2 power function going to be go faster to infinity than Ln. So that one's faster than this. X squared, bigger power, so actually Ln of x going to less than that, less than x squared, I mean not less than but slower, and power goes slower to infinity than exponential, and then so on. So and this ranking doesn't affect but when we multiply by a constant in front of it. And the reason we limited this to a positive constant, because if it's negative then it goes to negative infinity, where we don't want to say the roll rate. We said the roll rate is when it goes to infinity. Right. So the sequence, now we just have the proper definition of the limit, so there's not much here. So this is like when we count 1, we do a lot of limits before we define what is the limit of the function. So same thing here, we did a lot of limits and limit of a sequence, and then we say this is the proper definition of the limit. So limit, instead of using epsilon and delta in the definition of the limit of the function for a sequence, because we're not talking about the domain of x, it's not real numbers anymore, so we're not going to say we're not going to use delta. And also when we say limit of a sequence, we mean when n goes to infinity. So the limit of a sequence is the limit at infinity. So in that case, that's why we have n greater than n. So that means if n is big enough, the sequence is close enough to the limit values. That's what it is. And if the limit does not exist, we say the limit, the sequence diverges. If the sequence does not converge, we say set it to be divergent. Just grammar. Anyway, so in this section we find the limit of a sequence. Again, it's just a limit of a sequence, not a series. We have nothing to do with series here. We talk about individual terms here. Right. And this ranking will be extremely important. So have this with you when doing homework or test. Right. And then with that ranking would help us to find the limit. Not only do the ranking here, but help us to find the limit of this. Power is significantly less than exponential function, so bigger on the bottom, it goes to 0. So it helps us to find the limit that way too, not just ranking them. So that's why this is very important, so keep this handy. With that, I stop section 10.2 here. See you in another video in Calculus 2. And thank you for watching.